Dark matter is one of the most mysterious and least understood substances in the universe. Despite its invisible presence, it plays a crucial role in the formation and evolution of galaxies, including the Milky Way. Evidence for the existence of dark matter is based on a range of observational and theoretical data. One of the key observations is the rotation curves of galaxies. According to classical gravity laws, the rotational speed of stars at the outskirts of galactic disks should decrease as the distance from the center increases. However, observations show that the speed remains nearly constant, which can be explained by the presence of an invisible massive halo that increases the total mass of the galaxy. Another piece of evidence comes from the dynamics and morphology of satellite galaxies. Small galaxies that orbit more massive objects follow the same laws of motion as stars at the edges of galaxies. Analyzing the motion of these satellites shows that the mass of large galaxies is significantly greater than the mass of visible stars, confirming the existence of unseen matter. Additionally, observations of galaxy systems, from pairs to massive clusters, show that the total mass of the system is much greater than the mass of visible matter. The proportion of dark matter increases with the size of the system. In pairs, it is several times the mass of visible matter, and in large clusters, it is tens or even hundreds of times more. X-ray data on hot gas observed in giant elliptical galaxies and their clusters with the Einstein, Rosette, XMM Newton, and Chandra observatories plays a significant role in studying dark matter. The distribution of gas temperature and density allows scientists to calculate the mass of these objects. However, the mass of stars and gas is insufficient to hold the hot gas inside the clusters. When dark matter's influence is included in calculations, mass estimates and observations align. Analysis reveals that 80% of the mass of clusters is dark matter, 15% is hot gas, and the portion of stars is even smaller, around 5%. Gravitational lensing also provides additional confirmation of dark matter's existence. When light from distant objects passes through galaxy clusters, its path is bent due to the gravitational field of massive objects. This leads to distorted images of distant galaxies, sometimes even splitting them into multiple images. By studying these distortions, scientists can reconstruct the mass distribution inside the cluster. Research has confirmed that the ratio of unseen to visible matter aligns with data obtained by other methods. An exceptional case involves the observation of galaxy cluster mergers. A notable example is the Bullet cluster, where, during a collision between two clusters, the majority of the mass, dark matter, separated from the hot gas, baryonic matter. Observations revealed that the mass associated with gravity does not match the distribution of visible mass. This is considered one of the most convincing pieces of evidence for dark matter's existence. Similar behavior has been observed in other clusters like CL0024+17, MAX J0025.4-1222, and Abell 2744. In 2024, the merger of the MAX J0018.5+1626 clusters allowed for the first time the mapping of the velocities of both dark and baryonic matter, providing a direct opportunity to study dark matter. There are also theoretical proofs. Without dark matter, galaxies would not be able to maintain their stable shapes, as the mass of visible stars and gas is insufficient to sustain their rotational dynamics. Observations of cosmic microwave background, CMB, fluctuations also support its presence. Density fluctuations in the universe about 400,000 years after the Big Bang were too small, 10⁵, to form the large cosmic structures we see today. However, if dark matter is considered, these fluctuations could have amplified more rapidly, aiding the formation of galaxies and clusters. These observations and theoretical calculations indicate the existence of dark matter and its vital role in forming cosmic structures. But what if dark matter doesn't just hide in the universe, but actually causes ripples in spacetime itself? Could scientists catch it in action? There are numerous hypotheses about the composition of dark matter. In one recent study, scientists suggested that dark matter could be composed of ultra-light particles. Unlike traditional massive dark matter candidates, for example WIMPs, These particles may have properties similar to electromagnetic waves. If this hypothesis is correct, ultralight dark matter particles could create ripples in space-time fabric. These ripples would be similar to those caused by gravitational waves predicted by Albert Einstein's general theory of relativity. According to the theory, gravitational waves are fluctuations in space-time caused by the accelerated movement of massive objects, such as the merger of black holes or neutron stars. An intriguing aspect of this new hypothesis is the possibility of detecting dark matter-induced ripples using existing gravitational wave detectors, such as LIGO, Laser Interferometer Gravitational Wave Observatory. LIGO first detected gravitational waves in 2015, confirming Einstein's prediction a century later. Researchers believe LISA will have sufficient sensitivity to detect interactions with dark matter particles. The LISA mission is planned for launch in the mid-2030s, meaning the opportunity to test this hypothesis may not come for another decade. However, scientists are exploring other methods to search for dark matter. One such method involves analyzing the oscillatory effects of dark matter on space-time by observing rapidly rotating neutron stars. These objects possess extremely strong gravitational fields and high rotational speeds, making them ideal natural laboratories for detecting even the smallest disturbances in the fabric of space-time. Understanding the nature of dark matter is of fundamental importance for cosmology, as it determines the structure and dynamics not only of the Milky Way, but also of the entire universe. The question of its nature and origin remains open, and continues to be one of the biggest mysteries in modern physics and astronomy. What role do star clusters play in the formation and evolution of galaxies? How does their study help us understand the processes of star formation in the Milky Way? A star cluster is a visually connected group of stars that share a common origin and move together as a cohesive unit within the galaxy's gravitational field. There are two main types, globular and open clusters. Globular clusters are dense groups of stars ranging from hundreds to millions of objects. These stars are gravitationally bound and are typically old. In contrast, open clusters are less dense, younger groups consisting usually of a few hundred stars. However, over time, open clusters are disrupted by the influence of giant molecular clouds moving through the galaxy. Stars from disrupted open clusters may continue moving in the same direction, even if no longer gravitationally bound. If such stars continue to move as a unit, they are called moving groups of stars. While most stars in the Milky Way remain gravitationally bound to the galaxy and do not leave it, there are hypervelocity stars. These stars have velocities such that they will eventually escape the galaxy. The high density of stars in the centers of clusters leads to strong gravitational interactions, which can accelerate stars to very high speeds. In some cases, a star may reach the fourth cosmic velocity and escape the galaxy, heading into intergalactic space. Hypervelocity stars were theoretically predicted in 1988, before the existence of supermassive black holes was proven. In his work, Jack Hills proposed that supermassive black holes could accelerate stars to very high speeds, up to 4,000 kilometers per s. This phenomenon became known as the Hills mechanism. The first hypervelocity star was discovered by astronomers in 2005, and it was indeed leaving the center of our galaxy. However, many such stars have since been discovered, and often they are not aiming to leave the galactic center, but are moving in other directions. Currently, scientists have concluded that in addition to supermassive black holes, there are two other ways to accelerate stars to hypervelocities. First, a star may be accelerated by a supernova explosion in a binary system. Second, stars may gain high speeds through gravitational interactions within globular clusters. Research and computer models have shown that globular clusters are capable of accelerating stars to speeds reaching 2,000 kilometers per s. One of the most well-known hypervelocity stars is HD 271791. This star, with a mass approximately 11 times that of the Sun, was discovered about 3,000 light-years from the center of the Milky Way. According to computer modeling results, this star did not approach the supermassive black hole at the center of our galaxy, but likely originated from the outskirts of the galaxy. Astronomer Vasily Gvaramadze explained how the star acquired such a high velocity. According to him, its acceleration could have been the result of gravitational interactions between several stars. One hypothesis is that HD 271791 ended up in such an extraordinary orbit after a collision between two binary star systems, one of which it belonged to. Another possible scenario involves interaction with a massive star about 300 times the mass of the Sun. To confirm one of these hypotheses, according to the scientist, additional observations are required. Another example is the star US 708, located in the constellation Ursa Major in the Milky Way's halo. It is one of the fastest-moving stars in our galaxy. It was first discovered and studied in 1982 by Peter Asher and his colleagues from Pennsylvania State University, who identified it as a faint blue object in the Milky Way's halo. Later, in 2005, observations of this star were continued as part of the Sloan Digital Sky Survey. Star clusters serve as both birthplaces for new stars and sources of information about older stars. Observations of them help us better understand the dynamics and history of our galaxy. They are also important for studying the chemical composition and evolution of interstellar matter, which in turn allows us to reconstruct the process of star and stellar system formation in the Milky Way. How do local gas and dust clouds affect the movement of stars and the formation of new stars? How might the interaction between star clusters and interstellar clouds influence the future evolution of the Milky Way?